what are then the conditions and features that might affect errors? Here are some good examples of conditions that are worth remembering. One is going to be environmental uncertainty. So this is, again, going back to our classic Mintzberg idea of how well developed is knowledge, in this case, about the causes of errors in the field. And also environmental complexity, how easy is it to recognize anomaly? And also environmental stability, which is, are new anomalies or threats likely to crop up? So you could imagine when you're dealing with planes, for example, it may be that environmental uncertainty, i.e. we have a pretty good idea of what makes planes crash, relatively speaking, and we can also surveil that pretty well. But stability might be fairly low, as in weather can change quite quickly. And also maybe the environment in some cases is quite complex, in other cases it's quite well, relatively low complexity. So environment is clearly a big feature of in sort of three different aspects of the environment are very critical to understanding error rate and how in particular we can recognize and respond to anomalies. In addition, things like tempo or time pressure or difficulty, so anything that makes it harder to respond in quick work. Additionally, there's an issue that is associated with tempo or time pressure is the idea of close coupling of activity. So the extent that there's one activity that depends on another, you can have an error cascade that starts going very quickly, which against a small little problem like tripping on the deck might lead to a very big negative outcome, like a plane's actually crashing, because it's a very tight space on the deck of the aircraft carrier. And also, who is responsible? So if it's not always clear, if there's gray space, in terms of accountability or responsibility, there might be some piece of information that's known in one place, but then not communicated to another. In fact, this is really one of the key insights of understanding ICS, is to understand how gray space is, relatively speaking, eliminated through the ICS structure and also through the major ICS process of constantly reporting back conditions that might be associated with anomalies to the person who's in charge of the ICS commander. So again, if we remember back to this idea of stability and complexity, this is back from Mintzberg. So you can imagine that while we know there are no such thing as these pure prototypical forms, you can imagine that in much the same way we understood Mintzberg to say, the more complex the environment is, basically the more you need to delegate down to your frontline operating corps. The more simple it is, the more you can have something that looks like a machine bureaucracy, at least, right? Especially if it's also fairly stable. As it gets more dynamic, you might need to have more of a simple structure. So keep those things in mind as we look at these different cases of seeing that in part, organizations aren't always facing the exact same environment all the time. And part of what you might see is shifts across different organizational processes, depending on the sort of nature of the environment they might be facing for each of the processes. So what types of things might you see when you have environmental uncertainty or complexity? These are different concepts, but they in essence get dealt with in somewhat the same way. The biggest problem, of course, with uncertainty is it's much harder to address than complexity, even though they're quite related. So whenever it's low, you have an easier chance of detecting anomalies. You're more likely to be able to avoid a negative result. You typically can have very detailed manuals and procedures and rules, as opposed to a more general type of professional training in fundamental concepts. So the more complex an environment is, the more there needs to be on-the-ground responses to the precise environmental conditions. The more you need to have sort of general experts, as opposed to these very detailed manuals of exactly what do we do in this particular situation. So there'll tend to be more in-house training, therefore, as opposed to more regular updating and professional training in these different environmental conditions. There'll be typically often regular simulated practice with goals of avoiding errors when you've got, this is basically making response to these different conditions automatic. There's going to be some practice, but a lot of it is that's just years of experience tends to matter a lot more for predicting good outcomes in a high complexity or high uncertainty environment. So the more experience or practice that people have, but it can't be necessarily always simulated because of the very complex or uncertain nature. Now, there are attempts to build better and more complex situations, but that's a technological achievement more than an easy one. And again, we might think for Mintzberg, there's going to be less worker discretion in the case of low uncertainty or low complexity, and greater worker discretion in the case of higher uncertainty and higher complexity. So we can see then that there are features that help meet the requirements associated with this moderate level of complexity. In essence, for the ICS, this is these are sort of semi-unique events in the field where not all fires or hurricanes or other types of disasters are exactly alike. There is enough similarity and stability, though, in the environment that you can have training and rules can still be a foundation, as what you might find in low levels of environmental complexity, but there needs to be some constrained improvisation. Also, it's necessary because there's some degree of environmental uncertainty that as more is learned, as more of these unique events are basically there are lessons learned and other types of feedback and evaluation based on either incomplete successes or partial failures, that you can get updated knowledge and training available. So again, thinking back to also the Man Gulch, you could see that there were things like they changed training regimes, equipment provided, so for example, backup radios, etc. So a lot of things, as you have sort of one event that turns into that case an absolute failure, then you can learn from it, and so there needs to be upgraded training. For the naval air carriers, it's a pretty low complexity environment where it's very easy to detect anomalies, and so therefore you can rely on extensive in-house training and the NATOPS manual. So again, this is very much a machine bureaucracy type approach, as opposed, and not a lot of, again, necessarily updating. There might be need to keep your certifications up to date, make sure that you're still practicing, especially some of the rarer procedures, but it's not quite the same as there's actual changes in the way that there is in the ICS system. So the next condition that we need to pay attention to is environmental stability. So again, whenever you have a very stable environment, you're going to tend to have stable routines, specialization of labor, and pretty high degree of organizational hierarchy. More dynamic, we're going to tend to see more authority migration and flat authority structures as opposed to hierarchies. You're going to see a lot of environmental monitoring and rapid changes in activity. And one thing about hierarchy is it tends to create silos of communication. And so in a dynamic environment, you need to be able to communicate across levels of specialization. So you need to really avoid coordination neglect. Whereas in a stable environment, you can have some degree, basically formalized communication across silos within the organization, and it's not as big a deal. So if we were going to assess the ICS environment, we would see that there is a fairly dynamic environment, not very stable, that's being faced. And as a result, we see exactly what you would expect. An ongoing threat assessment is triggering role switching and structural elaboration. You're also seeing some degree of, in essence, authority migration. But so this is the command change process. And again, what you can see here is the best expert commander, that's closer to an authority migration type mechanism, exactly what you would expect to see under a less stable environment. Interestingly enough, with the naval air case, part of what you're getting is that there are actual, it's much more dynamic. It might be a low complexity, but it's much more dynamic. Changing weather conditions is one source of dynamism, and also just in some cases you have a much more demand-driven approach. So you have these sort of high-tempo moments in addition to emergency-type moments. So what you have to do here is we see continual monitoring, just what we would expect. Again, when you've got any type of dynamic environment, you're going to see a lot of monitoring. And the monitoring can trigger, instead of like role elaboration and well, it does actually triggering also authority migration. What you really see it doing is triggering changes in tempo and routines.